So motivated by our last video on the parabola and some interesting geometrical properties, especially those concerned with 3 points on the parabola and corresponding 3 dual points that Steven Choi and I published in COG some years ago. So motivated by that, let's have a look at the circle, sort of a natural thing to do, see if the same kinds or something parallel is happening for the other conics. And it's a kind of attractive situation, and I'm pretty sure that pretty well everything I'm going to be telling you here is probably known or perhaps even well known in certain circles, but it's generally not appreciated as much as it ought to be, right? These are interesting and very kind of natural things. So we're starting with a circle, okay, and 3 points A, B, C on the circle. The 3 lines determined by that triangle have poles with respect to the circle. So the pole of AB is this point X. The pole of BC is this point Y. The pole of AC is this point Z out here. So we get this external triangle XYZ, somehow dual to the triangle ABC of points on the circle. You can think of this triangle as consisting of 3 lines which are tangent to the circle, and this one here are 3 points which are on the circle. Okay, so maybe a first order of business would be to compare the areas of the 2 triangles here. So triangle ACB, there is 31, and XYZ is 53. And if we just move around, well, we see that, yeah, that external triangle can get very big. And of course, this one here is limited. So there's not going to be a relationship between the areas. That's fine. Okay. Now, I might turn those ones off, and we're going to be looking at 3 other triangles formed by just the individual side. So just this individual side AB has its dual or pole point here, and that forms a little triangle. Okay, so there's ABX, and BC together with its pole Y forms a little triangle. There it is there. And AC together with its pole Z forms a third triangle. There it is there. Okay, so this is parallel to what we did in the parabola case. We looked at these 3 sort of sub-triangles, if you want to call them that, these 3 sub-triangles individually, and looked at their some very simple triangle centers and see how those 3 of them connected. So let's start with, say, the centroids. Okay, so let's look at the centroids of these 3 triangles. And I'm using Geometers Sketchpad here, which is an alternative to GeoGebra. It's been around for quite a while. It's quite attractive. It allows me to conveniently sort of display and hide and show these various things. So this here in green, we have G sub X, which is the centroid of this triangle, G sub Z, the centroid of the big triangle, G sub Y down here, the centroid of this triangle here. Okay, so those are the centroids. Now, there's in terms of relationships, well, there's a kind of an obvious thing that sort of happens. If you join X and G sub X, it's pretty clear you're getting an altitude to this chord. So obviously you're going to go through the center. So that's going to be true also if you join G of Z and Z, you're going to get a line through the center, and Y with GY. So there's a sort of obvious perspectivity between this centroid triangle and the triangle XYZ. Okay, and sort of almost too obvious. We're not going to show it. But there's kind of another perspectivity that we might acquire in that direction. So instead of joining G sub X to X, we could also join it to C, which is the kind of the complementary point to the side here. So let's do that. Okay, so let's join G sub X to C, and G sub Y, which is over here, that's complementary to A, and G sub Z, which is complementary to Z. No, that was the wrong one. I'm sorry. Let me undo that one. We're going to join G of Z to what? To B, of course. Yes, to B. So we've joined, have I done that? Yes, okay. So I've joined G sub X to the complementary point C. I've joined G sub Y to the complementary point A, and G sub Z to the complementary point B. And these 3 lines that we get here in green don't coincide in a point, so nothing's happening in that direction. So that's fine. It's not that we get something every time. Okay, so that's the centroid, and in terms of its area, it's 14.20. Is there any nice relationship between it and this? Let's just move things around a little bit and see what happens. So that can also get quite big. So if there's a relationship, it's probably between that one and this one. And so one thing I could do is I could calculate this thing here divided by this thing. There it is there. We get 5.47. And as we move things around, we see that that ratio is changing. So that's not that interesting. Fine. Okay, so that was the centroid triangle. Let's get rid of that. And let's go back here so we can see our external triangle. And ACZ. Okay. Okay, now let's look at the triangle of orthocenters. Okay, so for example, ABX. This triangle here has orthocenter up here, O sub x. Okay, the meet of the altitudes. And BCY has orthocenter here. And the triangle ACZ has orthocenter here. Okay, great. So let's think about this triangle here. Let me turn out these ones off so they don't distract us. And just have a look at this. Well, if we compare it to ABC, we see something interesting. First of all, in terms of areas, the area of this orthocenter triangle equals the area of the original triangle ABC. That's cool. So there's a nice relationship between these two things. But in fact, if we stare at it, we see the relationship is much more than just that. These triangles are very, very closely connected. In fact, the sides are parallel. And they have the same area. These are actually congruent triangles, although their actual orientation is sort of reversed. But otherwise, they are congruent. See? The orientation is reversed, but they're congruent to triangles. It's quite cool. And of course, we can see that over here. The areas are the same, but the congruence is not so obvious at all. That's kind of cool. Another thing that we might want to do is to look at connecting the sides, the points of the original triangle with the corresponding orthocenters. So A sort of is associated to Y, so we could join A to O sub Y. We could join B to O sub Z, and we could join C to O sub X. And when we do that, lo and behold, we get some collinearity. So these two triangles are also perspective from this point here. Nice. And finally, let's look at the circumcenters. Okay, so these are the circumcenters of the three triangles. Like, for example, ABX, the circumcenter of this one, that's the center of the circle that passes through them. So it'll be a circle like this, with center C sub X that will pass through this triangle. And here C sub Y, it's the center of a circle that passes through B, Y, and C. And this is the center of the circle that passes through Z, A, and C. Okay, so, well, what about that? Well, if we look at its area, we see that it turns out it's exactly 1/4 the area of XYZ. Let's see XYZ. Okay, this one here is 1/4 that. And that means in terms of sides that this side here, well, actually we see it looks very much like being parallel to this one. This is parallel to this. This is parallel to this. These two look like they're similar triangles. Let's just see if that's true. So we move around. We see, yeah, that's what's happening. These two triangles are similar. Let me turn this one off. Okay, so XYZ and this triangle of circumcenters of the three subtriangles are are similar triangles, and they have this constant ratio between their areas. And finally, circumcenter perspectivity. If we join, say, C sub x, here's C sub x, with, let's move this around a little bit. Okay, here's C sub x. We join that with C. We join C sub y with A. We join C sub z with B. Then these three lines meet at this point. And so we see that these two triangles are also perspective from this point here. So that's just something that I sort of discovered playing around for a morning, okay? It's very easy to discover these kinds of things, sort of if you look in the right places. And so having something happening for one kind of conic, it's natural to look to see if the similar kind of thing is happening for other conics. And then, a little bit down the road, we could ask, well, is there anything like that at all happening for, say, cubics or maybe de Castellier-Bézier cubics? These are sort of natural questions to investigate. What about proofs of these things? Well, I could ask ChatGPT. I could say, look, take this triangle ABC and, give rational coordinates to A, B, and C in the usual way that we always do. And then you can calculate everything else that we've talked about in terms of the coordinates of A, B, and C. And you get these algebraic expressions. And all the facts that I've said here then come down to particular algebraic relations between these algebraic objects, which ChatGPT can do. And in principle, for a computer, this is like sadly, a second calculation at most, probably. Okay, so it's going to be the way of the future that more and more mathematics in terms of proofs is going to be sort of automated, and the AIs are going to start playing a bigger and bigger role. Maybe we still have a few years window being able to discover stuff that the AIs don't know yet, okay? But in 10 years, there won't be quite so much stuff like that lying around. The AIs will cover these territories systematically, in some crazy fashion, and present us with thousands of pages of spreadsheets and so on with all kinds of relationships. It'll be very disconcerting. So before that happens, opportunity to have some fun and discover some new things, and hopefully we'll be able to share some of these things in this new rational math hub that I'm slowly cooking up. Okay, so some interesting stuff to do here, and also interesting directions for more complicated curves.